So, welcome to module 22. In this module, we will introduce the concept of discrete random vectors. So, we have the following setup. So, suppose x is a p dimensional random vector, which is x1, x2, xp, and suppose this is defined on some probability space omega p, and suppose fx is the distribution function of x. So, I will say this random vector x is discrete if there exists a countable set Sx, which is a subset of Rp, such that probability x equal to x, small x is positive for every x in belonging to Sx, and the whole weight is given to Sx. So, that means probability x belonging to Sx. Since Sx is countable, this can be written as union of singletons. By countable additive property, this is same as summation x belonging to Sx, probability x equal to x, and this is 1. So, this definition is very similar to the definition for the one dimensional random variable. So, I will say that x is discrete if I can find a countable set Sx such that for every point in Sx we have a positive weight. So, probability x equal to x is positive, and Sx has the whole weight. So, that means probability x belonging to Sx, which is same as this, is same as 1. Now, under the notations of definition 1a, this set Sx is called the support of x, exactly the same way we did it in the case of random variables in R1. And this function fxx, which gives me probability x equal to x, that means probability of singletons, this is called the probability mass function of random variable x. Note that this function fx satisfies because it is a probability, so it is always greater than or equal to 0, and it is positive for every x in belonging to Sx because of this condition, and summation x belonging to Sx, fxx is 1. So, this probability mass function which satisfies these properties. So, let us see few quick remarks. So, let x is equal to x1, x2, xp be a p dimensional discrete random variable with support Sx, and suppose fx, small fx is the probability mass function, capital Fx is the joint distribution function. For given r greater than 0, let us consider this neighborhood of x and Rx, which is collection of all those t belonging to Rp, which is summation I is equal to 1 to p ti minus xi whole square is less than r. Now, these are p dimensional ball of radius r centered at x. For example, in the 2 dimensional case, it would be the interior and boundary of this circle, which is centered at x and has a radius r. So, this is the case in the case of r is equal to 2, because this is the interior of a circle, and in general in p dimension it would be a ball of radius r centered at x. Now, one can easily show that, as in the case of one dimensional random variable, the support of a discrete random variable is same as collection of all those x belonging to Rp, such that probability that x belonging to an Rx is greater than 0 for every r greater than 0. So, that is the Sx. It is straightforward too. So, I leave this as an exercise, which is a quick exercise. Now, the reason I am giving this exercise is because when we talk about continuous or absolutely continuous random variable, we will define support in this way only, because we have seen in the case of one dimensional random variable, probability x equal to x would be 0 for singleton x. So, there I will define support in this way. Now, since probability x belonging to Sx is 1, certainly probability x belonging to Sx complement would be 0. So, that means probability that x equal to x would be 0 for every x belonging to Sx complement, because probability of then this singleton would be contained in Sx complement, and since the probability of whole Sx complement is 0, probability of its individual parts would be 0. So, that is a small observation. Now, as in the one dimensional case, it can be shown that if there is a countable set S belonging to Rp and a function g from Rp to R such that it satisfies all the properties of a probability mass function, that means Gx is greater than or equal to 0 for every x belonging to Rp, Gx is greater than 0 for every x belonging to S, and summation x belonging to S Gx is 1. Then one can find a probability space omega p and a p dimensional discrete random variable defined on omega p such that G is the probability mass function of x. So, this kind of a remark we also saw in one dimensional case. Now, let us see another remark. So, suppose you have y1, y2, yp be a p dimensional random variable. for the time being I am not assuming that it is discrete or continuous, it is an arbitrary random variable, and suppose it has distribution function f phi, and suppose A is equal to A1, A2, AP is a fixed point in RP. I define AN as A1 minus 1 by n, AP minus 1 by n for n is equal to 1, 2 and so on. Then x equal to A event is same as x inverse of A, that means this is same as collection of all those omega belonging to omega, such that x omega is same as A. Now, this A can be approximated through intersection of these rectangles. So, I am taking their intersection. So, what is happening in, for example, let us look at in 2 dimensions, it is like this rectangle. So, this may be A, right, this may be A1 minus 1 by n, this is A1, this is A2 minus 1 by n and A2. So, when I am talking about x inverse intersection A and A, I am talking about this integral. Now, as n increases, this shrinks. So, this is would keep shrinking, and finally, what would happen is this approximating rectangle will become a singleton A. So, that is x inverse intersection n is equal to 1 to infinity A and A becomes x inverse of A. Similar things we did in the one dimension as well. Now, we know that x inverse of intersection is same as intersection of x inverse. So, this is same as intersection n is equal to 1 to infinity x inverse A and A. So, probability x equal to A is same as probability of intersection n is equal to 1 to infinity x inverse A and A. But this is a monotone decreasing sequence of events. So, by continuity of probability measures, this is same as limit n going to infinity probability of x inverse of A and A. Now, we know the formula of x inverse A and A in terms of the distribution function we derived in the earlier module. This is same as summation k is equal to 0 to p minus 1 to power k z n belonging to delta k p A and A f x z n. So, these are basically, this set is vertices of the rectangle A and A, where k of them are ANIs. So, this is what you get. So, what you observe from here is that means if you know the distribution function, you can get the probability mass function, probability x equal to A through this relationship. So, now, so using T, it follows that the joint probability mass function of a discrete random variable x is determined by its joint distribution function. Now, conversely, the joint distribution function of x, which is f x x, which is same as probability x belonging to minus infinity to x. Now, since probability x belonging to S x is 1, this probability is same as probability x belonging to minus infinity to x intersection S x. The reason for doing that is because minus infinity to x is not countable. By taking its intersection with respect to S x, it has become countable, and this is equal to this follows from the fact because probability x belonging to S x is 1. Since this is countable, I can write down this as countable union of singletons. So, those singletons would be in minus infinity to x intersection S x, and then probability x equal to t, which is f x t. So, this is what you get as f x x. So, that means if you know the probability mass function, you can get the distribution function. So, that means distribution function and probability mass functions can be determined from each other. So, thus, to study the probability function p x induced by a discrete random variable x, it is enough to study its probability mass function. Now, let A be any subset of R p, and suppose I am interested in what is the probability that x belongs to A. Now, again A may not be countable. So, I write down this as probability that x belongs to A intersection S x. This is possible because probability x belonging to S x is 1. Now, this set has become countable. I write down this as union of singletons, union x belonging to A intersection S x, x equal to x. Now, this is a countable union of disjoint sets. So, by countable additive property of probability function, this is same as summation x belonging to A intersection S x, probability x equal to x, which is same as x belonging to A intersection S x, f x x. So, what it says is I sum over only A intersection S x, which is same as I sum over S x, and I take, if x is in A, I take it as 1. So, I am summing over only in A. If x is not in A, I am not summing. So, which is equivalent to saying this. So, this is same as, so probability x belonging to A is same as x belonging to Sx, fxx I Ax, indicator function of x. Now, let us talk about this result which tells us how to find the marginal distribution functions from the joint probability mass function. So, this is the result. So, suppose x1, x2, xp be a p dimensional discrete random variable, and suppose its support is Sx and probability mass function is Fx. For fixed k belonging to 1 to p minus 1, let y is same as x1, x2, xk, and z is xk plus 1 to xp, so that x is same as yz. So, this whole x has been divided into two parts, the first k part, first k components which are x1, x2, xk, then remaining p minus k components which are xk plus 1 to xp. Now, for a fixed y belonging to Rk, let us say Ay is the set of all those z such that yz is in the support of x. So, for a fixed y, this collection of all those z such that yz is in Sx. Then the random variable y is discrete with support as Sy. So, when I am looking at a part of x, what I observe is the marginal distribution function is discrete, and support is collection of all those y belonging to Rk such that yz is in Sx for some z belonging to Rp minus k. And the marginal probability mass function would be given by summation z belonging to Ay fx yz if y belonging to Sy 0 otherwise. So, if you look at what it is suggesting is, if you have to get the marginal probability mass function, you look at the joint probability mass function and sum out the unwanted variable which is z, and that I have to do for fixed y. That is why this z has to be in Ay. So, for fixed y, my Ay is the set such that yz is in Sx. So, I am summing out the joint PDF, summing out the unwanted variable in the joint PDF for a fixed y. The proof is simple. So, let us look at x belonging to Sx. X belonging to Sx is same as yz belonging to Sx, but Sy has a definition that Sy contains all those points y such that yz belongs to Sx for some z belonging to this thing. So, here I am given that yz belongs to Sx. So, this would imply that y belongs to Sy because yz is belonging to Sx. So, what you get is x belonging to Sx event is contained in y belonging to Sy. So, probability y belonging to Sy would be greater than or equal to probability x belonging to Sx, but probability x belonging to Sx is 1 because Sx is a support of a discrete random variable x. So, what you observe is probability that y belonging to Sy is 1. Now, I have to get the probability mass function. Also, note that Sy is countable. Why? Because Sx is countable. Sx is countable implies that Sy is countable, because Sy is all those y such that yz is in Sx. So, the points in Sx only determine the points in Sy. So, that is the reason why Sy is countable. Now, let us try to see what is a probability mass function. For y belonging to Sy, so Sy was basically collection of all those y such that belonging to Rp, such that yz belonging to Sx for some z in Rp minus k. So, that is a definition of Sy. So, I look at y belonging to Sy. So, that means yz belongs to Sy for some z belonging to Rp minus k. So, probability y is equal to y is same as probability y is equal to y intersection probability x belonging to Sx. This is again due to the reason that probability x belonging to Sx is 1, which is same as probability y is equal to y intersection x is same as y comma z. So, yz belongs to Sx, but y has been forced to be small y. So, intersection small y comma z belongs to Sx, which is same as probability y belong is equal to y. Note that yz belong to Sx if and only if z belongs to Ay. That is very obvious, because if z belongs to Ay, and what was Ay? Ay was just let us go back and try to see what is AY. AY is collection of all those z belonging to Rp minus k such that Yz belongs to Sx. So, this is same as collection of all those z belonging to Rp minus k such that Yz belongs to Sx. So, note that Yz belongs to Sx if and only if z belongs to Ay, because if z belongs to Ay, that means Yz belongs to Sx. So, this part is obvious, and if Yz belongs to Sx, that means z has to be in Ay. So, that is why Yz belongs to Sx if and only if z belongs to Ay. Now, what has happened is your Ay is a countable set, because points in Ay are determined by the points in Sx. So, this can be written as countable union of singletons. So, union z belonging to Ay, Yz is equal to y comma z. By countable additive property of probability function, this is same as some z belonging to Ay, probability Yz is equal to Yz, which is same as some z belonging to Ay, Fx, Yz. So, for y belonging to Sy, probability y is equal to y is given by this expression. Note that for y belonging to Sy, so if y belongs to Sy, that means Yz belongs to Sx for some z. If Yz belongs to Sx for some x, that means Ay is non-empty. So, this set will be non-empty if y is in Sy. And for z belonging to Ay, if z is in Ay, then Yz is in Sx. So, Fx Yz would be positive for z belonging to Ay. So, therefore, probability y is equal to y is positive for every y belonging to Sy. Also note that if y does not belong to Sy, y does not belong to Sy, what does that mean? That means there is no z such that Yz belongs to Sx. So, that means there is no z which has this property, and that would imply that Ay is empty. So, y for y not belonging to Sy, probability y is equal to y is 0, because then you will be summing over an empty set over here. So, this would be same as 0 if y does not belong to Sy. So, if y belongs to Sy, probability is this, y does not belong to Sy, probability is 0, and probability y is equal to y is positive for every y belonging to Sy, and that proves the result. So, what it says is, if you have to get the marginal probability mass function, you sum out the unwanted variable in the joint probability mass function. So, there are marginal distributions. This also suggests that marginal distributions of discrete distributions are discrete, because we saw that the distribution of y in the last theorem was discrete. The above result suggests that to get a marginal PMF from joint PMF, one needs to sum out the arguments of unwanted variables in the joint PMF. So, very simple. So, to illustrate the application of last result, let us try to see this example. So, suppose z is equal to x phi has this joint PMF, fx phi is equal to c times phi if 1 less than equal to x less than equal to y less than equal to n, x y belonging to the set of natural numbers, 0 otherwise. Now, here n greater than or equal to 2 is a fixed positive integer and c is a fixed real constant. Find the value of c, find the marginal PMFs of x and y, find probability x greater than y, probability x equal to y, and probability x less than y. So, to see this, first note that my support of x y is nothing but collection of all those x phi such that x y belongs to n and 1 less than or equal to x less than or equal to y less than or equal to n. So, that is the support of Sx. Now, clearly if one has to look at the support of x, what would be the support of x? So, that means collection of all those x phi such that x phi belongs to Sx phi for some y. So, that means up to, if I take y to n, x can go from 1 to n. So, Sx would be 1 to n. What would be support of y? Support of y, again if I take x to is equal to 1, the values of y could be 1 to n. So, support of x is same as support of y, which is same as 1 to n. So, let us try to see this example. Now, this constant c would be determined through the fact that total probability has to be 1. So, this is what the support of z is given to be, which is support of x comma y. So, this z is same as x comma y. So, since this is a discrete random variable, z belonging to Sz f x y is 1. So, what is happening over here? The first argument is always less than or equal to second argument. So, what I do is first I fix the second argument over here, which is y, because this is same as f x y x y. So, this is positive only when, so f x y x y, let us look at this same as c y, if 1 less than or equal to x less than or equal to y less than or equal to n, 0 otherwise, and of course, here x and y have to be natural numbers. So, what I do is I take the total probability. So, this is same as summation z belonging to S z f x y is equal to 1. Now, what I know is it is same as c y under this range. So, what I do is I first fix y. So, y can be going from 1 to n. So, y is going from 1 to n. So, as a free variable y can go from 1 to n. Now, y has been fixed. For a fixed y, x will go from 1 to y. So, x equal to 1 to y, and c times y, that has to be 1. So, which is same as c times summation x equal to 1 to y, I am summing, that means 1. So, that becomes y. So, that becomes summation y is equal to 1 to n y square, and this quantity summation y is equal to 1 to n y square, you know, is a sum of squares of first n natural numbers, which is same as n into n plus 1 into 2n plus 1 by 6. So, that is the reason why c becomes 6 upon n plus 1 to n plus 1. Now, let us try to see what are the marginal probability mass functions. So, again let me write down f x y x y, c y if 1 less than or equal to x less than or equal to y less than or equal to n, x and y belonging to the set of natural numbers, 0 otherwise. So, we have seen that support of S x is 1 to n. In fact, by the last result, one thing is guaranteed, that marginal probability mass functions would be discrete. If it is discrete, the support for x we have seen is 1 to n. So, for x belonging to S x, f x x is same as probability x equal to x. Now, to get probability x equal to x, I have to sum out the unwanted variable y in the joint PMF. So, this is same as probability x equal to x, y is equal to y, but this probability is positive only in this range. So, for a fixed x, I have to sum y. For a fixed x, y can go from x to n. So, that is what is happening over here. For a fixed x, y is summed from x to n, and this is same as c of y. Now, this can be written as c times summation y is equal to 1 to n y minus summation y is equal to 1 to x minus 1 y, and that is what is done over here. C times sum of first n natural numbers, which is n into n plus 1 by 2, minus sum of first x minus 1 natural numbers, which is x minus 1 into x by 2. So, f x x turns out to be this quantity. I put the value of c, which is 6 times n into n plus 1 into 2n plus 1, and you get this. Now, similarly, I have to get the y, to get the marginal PMF of y. So, support of y is same as support of x. So, I have to sum out the x. So, for a fixed y, x can go from 1 to y, and that is what we will do now. So, for y belonging to the support, which is 1 to n, probability y is equal to y, that means I have to sum out the unwanted variable x, but for a fixed x, for a fixed y, we have seen that x can go from 1 to y. So, c times y, which is same as c times y square. So, therefore, the marginal PMF of y is this if y is equal to 1 to n and 0 otherwise. It is 0 other reason because only in sy it is positive, outside sy it is 0. Now, let us look at what is the probability x greater than y. So, to get the probability x greater than y, I have to sum the joint PMF over support and x greater than y. But for x greater than y, Sz is empty. So, that means there will not be any element which satisfies both of this. So, that is why this will be 0, because Sz we know is collection of all those x y such that 1 less than or equal to x less than or equal to y less than or equal to n and x y. So, when x is greater than y, there is nothing common with SZ. So, that is why this probability would be 0. So, let us see probability x equal to y. So, that means joint PDF, we have to sum x y belonging to SZ such that x is same as y, but your range is 1 less than equal to x less than equal to y less than equal to n. So, you have to sum out x equal to y. So, this is same as C of y, and y can go from 1 to n, because there will not be any. So, x and y both are same arguments. So, that means, and both arguments same could be 1 1, 2 2 and n. So, that is why y is equal to 1 to n y, and this turns out to be this quantity. Probability x less than y is very simple to find, because this is same as 1 minus probability x equal to y minus probability x greater than y. This probability we have found is 0. So, this is same as 1 minus probability x equal to y, which is 1 minus 3 upon 2 n plus 1, which turns out to be 2 n minus 2 upon 2 n plus 1. So, we have seen how to get the marginal probability mass functions of discrete random variables. So, what we have seen is, if you have a discrete random vector, then its marginal distributions are discrete, and to get the marginal distribution, what you do is you sum out the unwanted variables. Now, in the second part of this module, we will discuss the concept of conditional distributions.